All right, in this lecture we're going to start chapter 13, which is on universal gravitation. All right, so we're going to start with Newton's law of gravitation. This is just plainly stated to us. So the force of gravity is going to be equal to g, which is a constant, times two masses, so m1, m2, divided by r squared. All right, this is called Newton's law of gravitation. So what this is saying is that if you have two particles, as shown down here, let's say I have one massive particle here and a second massive particle over here, there's going to be this gravitational attraction between them. Now, before we were writing our forces equal to ma, but this was only, and we usually had this a was usually g when we were talking about gravity. We said, well, the acceleration due to gravity is 9.8 meters a second squared. However, that is actually gravity only at the Earth's surface. And it changes depending on where you are on the Earth's surface, what your altitude is, and if you are up in the sky or further away or even in orbit. All right, so this acceleration due to gravity is actually not a constant, it's a specific value for a specific location on Earth. All right, so this acceleration due to gravity is going to change. When you're talking about two objects, no matter what they are, there's going to be an attraction force, right? The force is always attracting, and they're going to be towards each other. So for instance, if I have these two objects, there's going to be a force from the second object on the first object in the direction of the second object, so towards this other object, as there also is going to be a force on the second object going in the opposite direction, but an equal force. So remember, Newton's third law says there must be equal and opposite forces when you have a force interaction. So when you have two objects that are massive, the forces on each other are going to be the same. And the masses of these objects don't need to be the same for the forces to be the same. So for instance, if I had the Earth and I had a satellite orbiting it, we know that the satellite is going to be a lot less massive. However, the force on each of the objects is the same. So for instance, let's say there was 100 newtons of force on the satellite. All right, the Earth is going to be pulling at the satellite with 100 newtons of force, and the satellite is going to be pulling at the Earth with 100 newtons of force. Right, they're going to be equal and opposite forces. However, the effect, right, the acceleration is actually going to be a lot less on the Earth because the Earth is much more massive. Right, so just thinking back to F is equal to ma, if you increase the mass with the same amount of force, you then must decrease the acceleration. Right, so even though the forces are the same between these two objects, the effect on the satellite is going to be a lot greater, which is why we say that the satellite is really orbiting the Earth. Okay. Let me also mention that this g value here, this constant, is a gravitational constant that was discovered through experimentation. Newton found that there was a relationship between the two masses and the radius of objects that are attracting each other, and he needed some constant to make the math work, right? To make everything work out. So we have 6.67 times 10 to the 11th. This is a value that does not change. This is the universal gravitational constant. And this value just basically, like I said, just kind of makes the equation work. And it also has units to it so that you end up with newtons in your answer. So for instance, you have newtons times meters squared to get rid of the r squared in the denominator, and then divided by kilograms squared to get rid of the kilogram squared from the numerator. Right? So the value that you end up, or the unit that you end up getting for force ends up being newton. This can also be written as meters cubed divided by kilograms second squared. All right, it works out the same. All right, so Newton's law of gravitation, a uniform spherical shell of matter attracts a particle that is outside the shell as if all the shell's mass were concentrated at the center. So basically what this is saying is, let's say that the Earth was a big shell. Like it wasn't a solid sphere like we know that it is. Let's say it was just a shell. So basically that means all of the mass is going to be on the outer rim of this spherical shell. Well, if you have an object outside of the shell, let's say over here, the gravitational force on this object is the same as if all of this mass that is distributed around the shell was located at the center of the shell. All right, so it really simplifies the problems. Instead of trying to figure out, let's say I was going to take the integral of this. Let's say I divided these into little differential elements all the way around. And then I tried to figure out what each of these differential elements effect on some particle out here was. That's a lot more complicated. It turns out that it's going to be the exact same as if all of this mass, all the differential elements, were located right here at the center of your spherical shell, right? Which really ends up simplifying the problem. Okay. Now, in the picture here, just to reiterate that equal and opposite force thing, we know that there's going to be a force on an apple that's on the Earth's surface, right? We can call that 0.8 newtons. And the apple is going to be pulling on the Earth with also 0.8 newtons, right? And that force is going to be located from the center of the Earth, right? We can simplify it and say that, well, we know that there's all these different atoms acting on this single atom or all the way through around the Earth, but if we took all the Earth's mass and put it right at the center, we can simplify that and say that is where the force is located. All right, so let's go to do an example. So the figure shows that an arrangement of three particles, particle 1 of mass 6 kilograms, particles 2 and 3 of mass 4 kilograms, and they're a distance of 2 centimeters away. What is the net gravitational force on particle 1 due to the other particles? All right, so we can go ahead and use Newton's law of gravitation. And we're going to do it by one particle at a time. So you can see what the gravitational force is from one particle and then add that to the gravitational force of another particle. But we just need to keep in mind that forces are vectors. So for instance, the vector is going to be in this direction from particle 3 and in this direction on particle 1 from particle 2. All right, so when we add those vectors together, we need to add them vectorially, not just straight up add them like they were a scalar. All right, so again, our Newton's law of gravitation, we're going to say, we're just look at the first particle, so it's going to be F12 is equal to G m1 m2 divided by r squared. All right, we're going to plug in the values. So it's going to be 6.6, let's go back there. 6.67 times 10 to the negative 11. And the units again are meters cubed divided by kilograms a second squared. And then then you multiply by our two masses. So we have 6.0 times 4.0. And we divide this all, and those are both in kilograms. And we divide this all by 0.020 meters, because it said it's 2 centimeters, so we want to make sure we convert that to meters. Okay, and we find that the force from particle 2 on particle 1 is going to be 4.00 times 10 to the negative 6 newtons. And since we're talking about a force, we want to make sure our units are in newtons. We're going to call this number positive because we know that this force is going to be going up in the y direction. So I'm just going to leave that as positive. Now we want to find the other force. So that's F13 is equal to G m1 m2 divided by, now this is going to be, actually I should say, this originally was a squared because they give you this value as a. So in the second one, these particles are 2a apart, so this is going to be 2a squared, making sure we square both the 2 and the a. All right, and then you're going to do the same thing. You're going to plug in these values, 6.67 times 10 to the negative 11. You're going to put in your two masses, which is m3 and m1, so that's again going to be 6 times 4. And then you're going to divide by 2 times, so it's going to be 0.04 squared. And then the value you get for that is 1.00 times 10 to the negative 6 newtons. Right, so we have our two forces. One of these should actually be negative because our second one here is going to the left. Right, the force is going to the left. So I can just put in a negative sign there. Now it's also important to realize that we can't just add these two together. These are not going in the same direction, so we can't straight up add them. We're going to have to use a squared plus b squared equals c squared. All right, so our net force, force 1, is going to be equal to the square root of F12 squared plus, the second one is negative, so it's F13 squared. We'll plug in our two values. The negative sign doesn't really have an effect because you're going to square it anyway. So our net force on 1 is equal to 4.1 times 10 to the negative 6 newtons. Okay? So now that I know the magnitude, I do want to find what the direction is. Right? This is what the magnitude of the net force is going to be. If I look at our graph here, or our picture, we know that it's probably going to be somewhere up in this direction in the second quadrant, because when you add the two vectors together, it should end up somewhere over there. To find the angle, all I would do is, since I know what the sides are, I can just do the tangent, or the inverse tangent. So it's just going to be the inverse tangent of f1,2 divided by negative f1,3, right, because there's a negative sign there. So this is just going to be the inverse tangent of 4.00 times 10 to the negative 6 newtons divided by negative 1.00 times 10 to the negative 6 newtons. And you end up with a value that is negative 76 degrees. Well, this is always from the positive x direction, since I kept all of my signs correct. So what they're saying is that the angle is somewhere down here, right? That the force vector is somewhere down there. Well, we know that sometimes with tangent we don't get the correct direction, so we really need to think about the problem. We know that it actually should be up and to the left. So if this is 76 degrees, and this is 76 degrees. So really, it's going to be 180 minus 76. So you end up with 104 degrees. So that would be this angle right here, 104 degrees. Okay. So let's look at gravitation near Earth's surface. So if a particle is released, it will fall towards the center of the Earth as a result of the gravitational force. With an acceleration, we shall call the gravitational acceleration. So we're just going to call this A sub g. Now Newton's second law tells us that magnitudes F and AG are going to be related by F is equal to MAG. Right? This is just Newton's second law. Right? And this is a subscript g. Now, if the Earth is a uniform sphere of mass m, so the total mass m, the magnitude of the gravitational force from Earth on a particle of mass m located outside of the Earth, a distance r from the Earth's center, is going to be given as such. All right, so basically what they're saying is we can simplify the total mass of the Earth. So let's say we have a really large mass of Earth, and then we have some object out here, a distance r away from the center. We can assume that all of Earth's mass is located right here at the center, so the radius away from the center of the Earth to this object will let us find what the force is on that object. Now, we need to make sure that we're including the radius of the Earth plus the height. So this is going to be whatever the radius of the Earth is plus h, which is the height above the Earth's surface. All right. Now, also, we saw that we can combine these two equations. So we can combine Newton's second law with Newton's law of gravitation and find what the acceleration due to gravity is. So if you look at this closely, if we set this side equal to this side, you get MAG is equal to G times big M, little m, divided by r squared. Again, big M is going to be the mass of the Earth, little m is going to be the mass of the object that's outside of the Earth's surface. All right, and then r is going to be the distance from the center of the Earth to that object. G is our constant. So we notice that these masses actually are going to cancel out, because in our F is equal to ma equation, this is the mass of the person, right? The mass of the person on Earth would give you what the force of gravity is. So this actually cancels out. So it turns out that the mass of the person actually doesn't even matter when you're looking at what the acceleration due to gravity is, which is going to be big G times the mass of the Earth divided by r squared. Okay. Now, any g value measured at a given location will differ from this acceleration due to gravity value before that location for a few reasons. We're not including some ideas in this, right? This is just if we had the mass of the Earth. However, the Earth's mass is not distributed uniformly. Right? So there's going to be a lot more mass near the center of the Earth and a lot less mass as you get further away. So it doesn't really work that we can make this assumption. Now also, the Earth is not a perfect sphere. It's actually a little bit oblate around its equator. So as it's spinning around, it's sort of throwing material out in this direction in a sense. So you get a little bit of oblateness out here at the equator. And which means over here it's actually a little thinner. Also, the Earth is rotating, so we have to think about rotational motion in all of this too, or at least consider it. All right, so for the same three reasons, the measured weight, which is mg of a particle, also differs from the magnitude of the gravitational force on the particle. All right, so this force mg isn't necessarily going to be exactly the same. It's going to be close, but it's not going to be exactly the same. All right, so let's look at this figure here. So a crate sitting on a scale at Earth's equator, as seen by an observer positioned on Earth's rotation axis at some point above the North Pole. B is, down here, they show a free body diagram for the crate with a radial r-axis extending from Earth's center. So the gravitational force on the crate is going to be represented by its equivalent mag. The normal force on the crate is given by Fn. So you have mg pulling down, you have the normal force pulling up. The normal force on the crate, because of the Earth's rotation, the crate has also a centripetal acceleration that is directed towards Earth's center. So not only do you have mg pulling down and the normal force pushing up, but you also have this additional acceleration going down towards the center of the Earth, right? Because of the centripetal motion. All right, so let's go and do an example. We can look at, well, are these differences in acceleration really relevant, and maybe where are they relevant? So an astronaut whose height, h, is 1.7 meters, floats feet down in an orbiting space shuttle, a distance r is equal to 6.77 times 10 to the 6th meters away from the center of the Earth. What is the difference between the gravitational acceleration at her feet and at her head? All right, well, we could approximate the Earth as a uniform sphere, right? So we'll just put all of the mass together at the center. Then we're going to have to use the previous equation, the gravitational acceleration at any distance r from the center of the Earth. So this is just our acceleration equation. Right, so our acceleration due to gravity is going to be equal to our constant times big M, which is the mass of the Earth, divided by r squared. Now, we might simply apply this equation twice. So we could look at the equation with r is equal to this distance, right, the distance away from the center of the Earth, which is where her feet would be, and then with r plus the length of the person for the location of the head. However, a calculator may give us the same value for the acceleration due to gravity because thus the difference of 0, right? Because you can't really tell because there's so many significant figures before it. So because h is so much smaller than r, right? This value here is so much smaller than here. It's going to be really hard to accurately calculate that. But there's a more promising approach because we have a differential change dr in r because the astronaut's feet and head, or between the astronaut's feet and head, we can differentiate the equation. So basically what this is saying is because this difference in height is so small, we can just call that an infinitesimal element dr. It's in the direction of r. It's some really tiny bit of r. So what we can do is take this equation and take its derivative. So when you do that, on the left side, you just have the derivative of the acceleration, which is kind of what we're looking for, right? We're looking for what the difference in the acceleration is between a closer point and a further point, all right? And then that's going to be equal to -2, because this is, let's see, if we draw it up here, really we're taking the derivative of r to the negative 2. So when I do that, I pull the coefficient out front, so I pull out the negative 2, and I subtract the exponent by 1. All right, so it's really negative 2 times r to the negative 3. So what that ends up being is negative 2 times g times the mass of the Earth divided by r cubed now, because r to the negative 3 is 1 over r cubed. And then since I took the derivative, I have the little dr there. Okay, so this dAg is the differential change in the gravitational acceleration due to the differential change dr and r. So that's what we're looking for. Now, for the astronaut, this little dr here is actually h. It's the height of the person. That's that little tiny bit that we're talking about. And we know that r, of course, is going to be this big radius. So plugging in these values, we get that our differential change in g is going to be, or our acceleration due to gravity, I should say, is going to be negative 2, 6.67 times 10 to the negative 11, 1.99 times 10 to the 31st, which is going to be the mass of the Earth, so this is in kilograms, divided by this radius, so it's going to be 6.77 times 10 to the 6th meters, and this is going to be cubed. So you get a value that's negative 4.37 times 10 to the negative 6, and that's going to be in meters a second squared. All right. So this is the difference in acceleration for someone that is floating up in the, or an astronaut that's floating up in space that's relatively close to the Earth, between his head and his feet, which is really tiny. I mean, we know that the acceleration due to gravity on Earth is 9.8 meters a second squared, so this tiny little bit of change you're not going to be able to feel. Now, what if the astronaut is now feet down at the same orbital radius about a black hole, which is about 10 times the mass of a sun. So it's 1.99 times 10 to the 31st. Oops, sorry, I just realized I made a mistake. This, I put in the wrong mass here. I was looking at the wrong problem. So this should be 5.98 times 10 to the 24th kilograms. I knew that number looked a little big. All right, so that works out better. Oops. Okay. The value still ends up being the same. So now we're looking at, well, what if we were close to a black hole? Right? Would that have an effect? And we can go and do the same calculations that we did before. So we're going to take our acceleration due to gravity, the derivative of that. This is going to be 2 times, and then we have the gravitational constant. Then we have the mass of this black hole, which is 1.99 times 10 to the 31st kilograms. And we divide this by, again, the radius cubed. So 6.77 times 10 to the 6 meters cubed. Right? This whole thing is multiplied by 1.70 meters. I also forgot that down here. 1.70 meters was the height. Right? This dr over here was the height. We need to make sure we add that in. Okay, so when we solve this out, we get a value that's negative 14.5 meters a second squared. All right, so now there's a difference in acceleration between your head and your feet of more than the gravitational attraction of Earth. Right, so this means that the gravitational acceleration of the astronaut's feet toward the black hole is going to be noticeably larger than that of her head. And the resultant tendency is going to be to stretch her body, would be unbearable and quite painful. So if he drifted closer to the black hole, the stretching tendency would increase drastically. All right, so it sort of gives you an idea of kind of what is happening near a black hole. All right, so the last thing we want to cover is, well, what if you were trying to find what the gravitation inside of Earth was? So if we have a uniform shell of matter, it is going to exert no net gravitational force on a particle that's located inside of it. So basically what it's saying is, if I had this Earth shell that we were kind of talking about earlier, and I was somewhere inside of the shell, let's say maybe at this point here, any gravitational force from all of this is going to cancel out. So what that means is there's going to be, again, if I divide these into a whole bunch of different elements all the way around, the stuff over here is going to be pulling outwards at this object, and the stuff over here is going to be pulling sort of inwards, like inwards towards the center of the Earth in this direction. So all these vectors end up canceling out. All right, so if you're inside of this sphere, you don't need to worry about any mass in the shell that is outside because it's all going to cancel out anyway. All right, so let's look at this problem. So 3 explorers attempt to travel by capsule through a tunnel directly from the South Pole to the North Pole. According to the story, as the capsule approaches Earth's center, the gravity force on the explorers becomes alarmingly large, and then exactly at the center it suddenly, but only momentarily, disappears. When the capsule travels through the second half of the tunnel to the North Pole, so check this story by finding the gravitational force on the capsule of mass m when it reaches a distance r from the center of the Earth, and assume that the Earth's sphere is of uniform density ρ, all right, which is mass per unit volume. So ρ is the mass of the Earth per volume, right, the volume of the Earth. All right, well, I can use Newton's law of gravitation to think about this. So we can say that the force is going to be equal to g little m, which is going to be the mass of the capsule and the people, times big M, which is the mass of the inside of the Earth. So it's only the mass that is actually inside of the sphere that they're actually on. We're not worried about any of the mass that's on the outside. And this is, of course, divided by r squared wherever they happen to be. Well, like I mentioned earlier, the mass of the inside is just going to be the density times the volume. Right, so really in this equation, I want what the mass of the Earth is inside of a specific volume. So if I just multiply v by both sides, you see that the mass of the Earth is equal to its density times its volume. Right, and this is, again, just the volume of the inside of the Earth. And we can find the volume simply by the equation 4 pi r cubed divided by 3. Right, that's the volume of a sphere. Right, on an AP test, they would certainly give you this. And we can go ahead and take this mass of the inside and plug it into our equation. So that it turns up, or this turns out being 4 pi times our constant times little m times the density of Earth divided by 3 times r. So we should notice that when you're inside of the Earth, the force actually is a linear function. Right? It only depends on r, which is your distance away from the center of the Earth, when you're inside of the object. Right? It does not depend on the inverse square, as we would thought. So basically what this is saying is the closer and closer you get to the center of the Earth, the less and less gravity the force of gravity you're going to experience. Right? Which is sort of counterintuitive to what they said in the story here. Okay, that's it for this lecture. We will pick it up next time.